Well, the problem for the computer is that the voltage and the currents unknowns and the partial derivative terms also, ddt and ddz, are written for continuous space and time. Meaning analytically we can solve for them anywhere in space and time, but we can't use a computer to store unknown values at any possible positions in space and time. We have digital computers, and that means we can only solve for unknowns and the derivatives of our unknowns at discrete positions in space and time. So this means we need to convert these equations to discrete space and time. And so how do you think we might go about doing this? Well, it helps to learn and get ideas from what others have done before us. That's where really a lot of people get ideas in general. When we have problems, we can look and see what others have done before us for similar types of problems. So what we can do is look up how people currently solve. These are coupled differential equations. So we can look at how people solve these types of equations in the time domain, where as opposed to the frequency domain. We're solving these in time, watching these voltages and currents propagate around. And we could start with talking with colleagues. We could also perform a web search. We could look at, if we look at time domain, if we were to search and then partial differential equation, we could also add in numerical method. We could add in the word electromagnetics. We'd have to write that out. But if we started to do these kind of searches, we could quickly find out that the most popular method for computational electromagnetics for the time domain is what's called the finite difference time domain method, or FDTD. So this is the finite difference time domain method. Now, FDTD is specifically for solving Maxwell's equations. We have Ampere's and Faraday's laws, which we'll discuss more later this semester. But it turns out that Ampere's and Faraday's laws, which you can see here, for an electromagnetic wave traveling in the z direction, so this is written in the same, one dimension. We have the unknowns only changing in one dimension, the z direction, and in time. And they have an analogous form as the telegrapher's equations. So there's partial differentiation with respect to space and time. You can see that here as well. The unknowns are different. Here we have a vector h pointing in the y direction, an electric field pointing in the x direction, but they're same kind of form of these equations. So in other words, numerical techniques that we can use to solve Maxwell's equations, which is FDTD, we can see if we can apply it here to the telegrapher's equations. And if we were to study the FDTD method, we would find that FDTD can help us to figure out where to position our unknowns. In our case, we have V and we have I. And where to position them in space and time, because we have discrete positions where we'll be storing them. And also how to solve the partial derivatives. And it turns out we'll use what is called central differencing, which we'll talk about in just a second. And actually right now. So what is central differencing? Well, when we first learned about differential equations in math class, we were taught that the derivative, or the differential, it's the slope of the line. So if we take some function f, df, dx, partial derivative with respect to f prime, we learn that this is the slope of the curve. But when you have discrete points, there are many different ways to find the slope of the line. So I'll say here, many solutions when we have discrete points as opposed to a continuous line. So let's draw a curve with 3 discrete points. Let's see. This will be with respect to space. We have f, it's a function of space, and we're going to say this has that kind of shape, but we have a discretized space. So we're going to say we have 3 different values stored. This would be at position z, the ith value of z. This would be zi plus delta over 2. So I'm going to say that this total distance is delta z. So actually, I meant to say delta z over 2 here. Delta, okay, so then this one would be zi minus delta z over 2, a little bit of a distance to the left. And so if I were to draw, we're going to talk about 3 different ways that you can obtain the slope. And one is this. We have forward differencing means we would use a value that is to the right as well as the value right at zi. So we want to evaluate the slope right at this location. We could use a discrete point to the right as well as the value at that location that we want the slope at. Or another option, we could use backward differencing, which we would use the value at the location where we want to obtain the slope, and also one to the left. Or another option is to use what's, I should label that. So this would be backward differencing. And then the last option we'll talk about is what's called central differencing, which is where you use, to get the slope at this location, you use a discrete point, one to the left and one to the right, a delta z total distance apart from each other. Here is that plot again, and then numerically, or if we want to write out the slope of the derivative with respect to z of I, if we use forward differencing, we'll say this is about equal to, because it's an approximation, f at position I plus 1 with zi plus delta z over 2, so one value to the right, minus the value at which we want the slope at the location, and divided by delta z over 2, because that's distance away from each other. This is the forward differencing approach. Another option is backward differencing. So that has a similar format. We're going to have f of I minus fi minus 1. That would be this one right here, and this one, which is right there. And that's also delta z over 2 apart from each other. So this is backward differencing. And then for central differencing, which is the one we'll be using, we approximate derivative as being f of I plus 1 minus f of I minus 1 divided by the distance between them, which would be a total of delta z. And from these 3 options, if we were to analyze them and how accurate they are, which is something we do in another course that I teach, 5340, 6340, it's on numerical techniques for electromagnetics. We could look into this more. Here for this lab, I'm just going to tell you that central differencing is more accurate than the other 2, than forward differencing and backward differencing. And it's also fairly simple, still fairly simple to implement. I mean, there are certainly other approaches we could use, higher order methods that use more points in the curve to approximate the derivative. But this is much simpler to implement. It requires less calculations. And so this is why FDTD uses this approach. So we're going to be using the central differencing approach. So now we need to turn the telegrapher's equations into difference equations. So we're going to use central differencing. And we need to apply that. Here's the first telegrapher's equation. We'll start with just one of them. So we need to do 2 things. We need to discretize the unknowns being voltage and current. And we also need to write the partial derivatives as central differences. Or we need to approximate them using, so maybe I'll say here, approximate partial derivatives, and I'll say using central differencing. So go ahead and try to do this for the first telegrapher's equation. You might need to change a bit your notation of how you want to write this, so using discrete points instead of continuous points. Just give it a try, and this one as well, using central differencing, which means you'll also have to decide where to position the voltages and the currents. So just give it a try, see how far you get, and we'll then go over it.